afternoon session will last than 2 hours from now to 3:15 minutes approximately, British summer time. 4 teams will present their outcomes for 20 minutes each. The projects introduced now are especially focused on Copernicus activities at the ECMWF. So what is the nature of these projects? We will learn about the ADC Toolbox, which consists of different scripts in Jupyter notebooks, aims to compare atmospheric compositions datasets. The second project, named Elfridge, is an advanced compression technique for big data of Copernicus Atmosphere Monitoring Service, CAMS. The third project, is named MaLePoM, has developed a machine learning model to estimate emissions. The last project, named AQ Bias Correction. The developer teams has trained an algorithm able to correct bias in the CAMS model forecast for air quality variables. Next slide, please. We use the platform Slido to list the questions you would like to ask. Please, if something's in your mind, if you want to raise a question about the project itself or about the experience in the ESOC journey to the participants, I encourage you to go to slido.com and type the event hashtag you can see on the screen, ESOC 2021. It goes an interface where you can anonymously or write your name if you want and write the question in the box. The teams can answer just immediately after the presentation or at the end. There will be a 10-minute turn for answer and questions. So now I'm very happy to present the first project, the first team, which is formed by Alba Villanova Cortezon, which is based in Germany. The name of the project is ADC Toolbox, comparing atmospheric composition datasets. So I'm over to you, Alba, when you're ready.
Thank you for the introduction. My name is Alba, and as Esperanza explained a bit, I'm going to explain the final result of my project, which consists of the development of a toolbox that is mainly created with Jupyter notebooks to compare atmospheric composition datasets from different sources. As you can see already in this slide, the main sources that the main datasets that I have been using are the CAMS model, Stropomy sensor, EASY sensor, and GOME2 sensor from MaLePoM. Next slide, please. So just to give a bit of an introduction about me, it's going to be short. I come from Spain, and I studied my bachelor's degree in the University of Lleida. It was in mechanical engineering, and during the last semester and the last year actually also, I spent some time studying and working in South Korea. And I later came back to Europe, and I started studying a master's degree in geospatial technologies, which is an Erasmus Mundus program. And I'm currently officially studying at Nova University of Lisbon, where I'm writing my thesis actually about this project. But I've also started to work in Switzerland as a software developer intern at a company that is called Meteoromatics, which works with meteorological data. I have been doing this project for this program with the support of my mentors, which were Antti Ines from ECMWF, Federico Fierli from UMETSAT, and Michael Rasinger also from ECMWF, which I actually want to thank a lot because their support was really, really important for the development of this project. Next slide, please. So just to start a bit with the motivation of this project, basically the idea came from ECMWF, and they had 3 main objectives behind this development. First of all, they wanted to validate different data sets. So it was very important to know if some data sets from some satellites were accurate when comparing them to CAMP's model, which was developed by ECMWF. Once these data sets are considered valid, which is something that is going to happen after this project, well, they will check. I mean, the idea of ECMWF is that they can have more coverage of data, and then finally, once everything is implemented, the idea is that it's possible to detect anomalies and problems in the data sets when comparing them against each other. And so, well, these are the main motivations, but actually there is a problem behind the whole comparison, which is that it's not trivial, since the metadata is not similar at all between data sets, and these data sets are usually stored in different formats and also in different they actually have different resolutions, as I will explain in the next slide. So these are the sources that I have been using for this project. So we have CAMP's model from ECMWF, and I actually used the forecast dataset, and I also used the monthly means dataset. And so I got the following atmospheric components that you can see on the third column, and we can see that the data for CAMPs is always gridded, and it's actually not so heavy compared to the sensor data. Continuing with the other datasets, we have data from stropomy sensor, which is non-gridded, and it's usually daily. We can see here the file size, which is 60 megabytes, and that only corresponds to a part of the track of the satellite, which would be in Europe. So actually this stropomy is actually very, very, it consumes a lot of resources of the computer when trying to handle this data, and this makes the comparison against CAMPs very slow. Then we have GOME2 and EASI data. These both sensors have gridded data, and they give information about monthly means. And they also have non-gridded data, which is also more complicated to handle. We can see already on the right also that the file formats are always different, and they can range from grid to NetCDF to HD5P. We also see in the columns in the middle that the horizontal resolution is also not common in any of the sources, and yeah, that would be it. Now, currently, this toolbox that I created can compare CAMP's forecast against stropomy and GOME and gridded data, and also CAMP's monthly means against GOME and EASI monthly data sets. Next slide, please. So to explain a bit more about the code structure, we have this basic structure. So we have a folder, which is data, which basically the code uses this folder to store all the data sets, because it's possible to download them and so on within the Jupyter notebooks. Then we have a folder called functions, where we can find all the functions that are related to general issues, such as the match of the data, the units conversion, and the plot visualization. And then we also have 5 more files that have only the functions that refer to each data set. So we have functions CAMS, functions GOME, functions EASI, and functions stropomy. Finally, we have these examples, which I called main. And basically here we can see how to combine the different functions to get all our final results for each of the possible comparisons that we can make. Next slide, please. Here, I wanted to show a bit of the workflow. So once we get into one of the main files, we are going to run all these following instructions, let's say. So the user can run, should first install the software, obviously, and then he will be able to run the imports and also the related functions. Then the user can define a component, an atmospheric component, the sensor name and the model, which is always comes for now. And then the program itself is going to tell the user if this comparison is possible or not. Since we have that sometimes there are some atmospheric components that are not available from some sources. So it's important to check this before we move on, because it's not going to be possible to download the data. Once this comparison is possible and it's checked, the software is going to generate folders to store this data under the data folder. Then the user can define the subset, special extent, and the search period. That's only for the download of data, so it's not for the final plots. When you want to get the final comparison plots, you can redefine this special extent and the period also, which should be obviously within the bounds that you initially defined in the 5th step. Then the software is going to download, read, and convert the units of the data sets. It's going to subset them in smaller regions, and it's going to match the levels data if it exists. So we find sometimes that the data sets have total columns data, or they can also have partial columns data, or partial levels. I don't know exactly how to call it. But in this case, the first part of the program is going to match this levels data. It's going to interpolate vertically, and it's going to find the nearest neighbor to the in the CAMS model at the sensor grid. Then, and this is only for stropomy, the averaging kernels can be applied. So this is in principle something that improves the CAMS model, and currently is having some errors that we have to check, but this is a functionality that is almost finished. Then it's possible to merge the total columns and calculate the difference. So you basically finally get a table with all the coordinates and the values in each of the data sets and the difference. Then, as I said before, the user can define, again, the plot spatial extent and period. And depending on this definition, the maps are going to show differently. And also, the user will be able to visualize the scatter plots that are adjusted to that spatial extent of that period. And yeah, finally, the user would get the final results, which I'm going to explain in the next slides. So for the main results, I made here a list, more or less, of what we can get after we match the data sets. So first of all, it's possible to visualize these data sets in maps and also observe the difference in different parts. It's also possible to get the merge table that I call, which is the place where you see all the values. And it's possible to get a descriptive statistics table with information about the mean and standard deviation of the variables or the position. Then I created a function only for, I created a function for to be able to retrieve a specific data for specific coordinates and get a time series to see how this component varies in different places or locations. Later, as I mentioned before, you can get maps by the bounding box that you defined at the last steps or by different times. You can also get scatter plots and histograms also by the bounding box and by country, season, or time. And finally, you can get these results aggregated or individually, so you can analyze a bit better the differences. Next slide, please. Thanks. So here I will show you a bit of which plots do we get. And the first one that we have here is the comparison between CAMS model and stropomy sensor. This is level 2 data, so it's not very preprocessed. And actually, this data was kind of difficult to read and to subset because it comes in the data comes by scanline and ground pixels. It does not come by coordinates. Although it has auxiliary coordinates, it's not possible to retrieve these data from by giving coordinates. So that made everything a bit hard. And then, well, here we can see an example for nitrogen dioxide over Czech Republic. And as you can see on the top, it's also possible to compare ozone data, sulfur dioxide data, and carbon monoxide data. Next, please. Okay, so here we have an example of monthly means. So here we are comparing the CAMS reanalysis monthly means data with the ASI level 3 data, which is already pre-processed and comes in a grid. So it's easier to compare and to handle. And we see that we can do this comparison for ozone and for carbon monoxide. For this case, specifically in September 2020 over Europe, we see that there are actually big differences between both data sets. And it would be interesting if someone could, I don't know, some researcher could check more months and see the differences. I will go back to this comparison later. Next slide, please. Then we can also compare the data from GOME2 level 3, which is also gridded, and is basically, we only have nitrogen dioxide in this case. We can see that there are some missing values for GOME in this specific map. I've used the data from method B, so I did not combine it with method A, but it's possible to do that. And yes, that's another example. We can go to the next slide. And then we have this other example. I would say this one was one of the hardest because we have, as you can see, a global data set that is level 2, so it's not very pre-processed, and we have data for different satellite tracks. And it's very important to match this data with CAMS by time, and that's actually something that gets complicated when you are initially handling ungridded data, and then you want to grid it, because in the moment you grid it, you change the coordinates, and the times, you have to kind of grab these times from the ungridded data set to the gridded data set. And so there is kind of a mismatch with the times. We have that for CAMS, we have the lead times. I've got the lead times at 00, 6, 12, and 6 p.m. And for GOME, we have many other different times. So I'm actually matching the data by the nearest timestamp. And that can explain why we have some big differences in some areas of the differences plot, in this case, which is for ozone. And I combine the data from the 3 satellites, method A, method B, and method C. And yeah, it's possible to do this and also to visualize everything in different projections for nitrogen dioxide, ozone, and formaldehyde. Next slide, please. Here we can see an example of what I meant before by the retrieval of data by specific location. So this is for EASI. This is the data set I showed before. And it's for carbon monoxide, comparing it to the CAMS model. So we basically can input 2 coordinates or a list of coordinates, and we will get a table with the nearest latitude and longitude to those coordinates. And also we're going to get the value by each time. So at the end we can plot it and we can see some specific differences. Here we see, for instance, that in April there was a big peak of carbon monoxide. And I think that's quite interesting to see for different locations, to see if this is happening or not, if spring is a bad month or is it not. Next slide, please. So here we can see the scatter plots I also talked about. So you can see we can actually plot in different colors each timestamp. So we can see more or less the variations. And we can get also data about the linear regression, such as the coefficient of determination or the intercept of the coefficient of equation. And we can also see the distribution of these values in histograms. Next slide, please. And here we can see a summary for winter, spring, summer, and autumn. So all the stations and all the seasons, sorry. And the thing with this is there is something here I didn't think about, which is that the seasons are not defined in the same way in all the parts of the glove. So I actually will have to correct this, because now this is actually realistic only for the north part. And it can be applied to Europe, but it cannot be applied to Australia, for instance. So that's something to work on in the future. Next slide, please. And we can also see the results by countries. For this, I have been using Google API, and we can see there are less points because I only used 1 month. And that can be interesting in case you want to analyze a specific country. But in case you don't want to, you can just use a bounding box to approach the study to a specific area. And that's going to be more simple, and you will not need to use any resource to make the reverse geocoding, which would be getting the name of the country by coordinates, because we're always working with coordinates. We are never working with countries' names. So that's something that I applied at the end of the project. Next slide, please. So here we can see 3 examples of the tables we can get about the linear regression. We can get these tables by time, and we can get them by season or by country, also by different bounding boxes. So that's also interesting to have as at the end to get some more details, some more detailed data. Next slide. Thank you. So just going into conclusions, I would like to say that about this package that I developed, there are still many things to improve. I would say that the first thing that matters now is to correct the application of the averaging kernels, because it can be something that is going to be used and is going to be pretty useful, I think. And apart from this, it would be interesting to include other data sets. And I was thinking lately that it would be also interesting to compare the satellite data to ground observations somehow. So that's something that's on the works for later. Since this is part of my master thesis, I will actually continue working on this until at least January next year. So yeah, I will see what's the direction, and I will commend this to my mentors, obviously. But yes, for now, the next data set that we're going to include is the ASCII level 2 data, which we parked now, but I can do this soon. And then I would also like to give some conclusions about this program itself. It has actually been very challenging sometimes because the data sets were not easy to handle, and because my background was not atmospheric sciences, it was actually a bit hard for me. But it was also very rewarding, and it actually oriented me in a work direction where I would like to continue being on. And I also would like to say that the support from my mentors has been definitely essential to understand and develop this project, as well as the resources that they gave to me, because without the server, for instance, I would not have been able to run the code fast enough. So these are things that I wanted to point out. Next slide, please. For the future work, as I mentioned, I would like to include more data sets. The next one is going to be the ASCII level 2 data. Then I would like to correct the applications of the averaging kernels. I'm interested on adding animations, because now it's possible to see the variations on time, but it's not in the same space. So I would like to be able to visualize this easily. Then finally, I would like to add a revealing function, which is going to help to compare the satellite data sets among themselves. And then if you have any other suggestion, I would also like to listen to it, and probably I would try to include it. Next slide, please. And that's it for my presentation. Thank you so much for your attention. If you have any question, you can write it in Slido, or you can just ask me at this moment. Thank you.
Thank you very much, Alba, for taking part in ESoC, for your great presentation and for your amazing results. So if someone wants to raise a question to Alba, could you go to a Slido and type your question there? Thank you. Now we'll pass to the second project of this second part of Final ESoC Day in the afternoon session, which is Elfridge compressing atmospheric data into its real information content. The developer behind this project is MaLePoM from Germany, or from UK. Sorry about that. And it's in fact a follow-up of the project that started in ESoC 2020. So please, the floor is yours, MaLePoM, when you're ready.
Thanks, Esperanza. Yeah, when you move countries, then at some point both are correct, I guess. Welcome everyone. My project this year was compressing atmospheric data into its real information content, which is actually a follow-up project from last year. So we basically developed first ideas last year and went into more details this year. So this is work that has been mentored by Miha, Juanjo, as well as my two PhD supervisors, Peter and Tim. And so I'm a PhD student just about to finish up in Oxford. And really what how I would like to illustrate this problem today is, as you can see on the next slide, it's almost like a trick question, because I want to ask how far is it for someone to get from London to Paris, given the information that you see on this map. Think about it for a second. Really, like you see there's like 339.25 kilometers. And if someone asks you that question, what would you answer? And as you can see, next slide, please. As you can see, there is basically a lot of uncertainties, considerations that you have to take into account in order to know what you will communicate to someone, right? So the question is, where does someone come from in London? Where does someone go to in Paris? What is the means on the way? Are there any deviations? And so I guess in many cases, next slide, you will actually end up with something, communicating something, let's say like 350 kilometers. Because what's actually, if you ask that question, what's actually happening in your brain is that you see this number, you know that it can't be accurate to 10 meters, it can't be accurate to 100 meters, because you already in this map, you can see that there's a lot of uncertainty about where someone in London comes from, where someone in Paris goes to. And so basically your brain automatically incorporates this information about uncertainty and tries to round the value automatically to something that your brain considers to be somewhat accurate, somewhat real. And this is a very typical problem that we have in data compression. And this is exactly what we've tried to tackle with this project. As you see on the next slide, data compression in general is a trade-off. It's a big trade-off because if you have a big data set, you could either say like, okay, let's keep the data set as precise as possible, but then it's going to be really big. You can't necessarily reduce the size as much. If you want to reduce the size, you may end up with something that is not as precise anymore. Or if you've reduced your size, it may take ages to decompress it again to basically regain what the original information that you started from. Data compression has been applied to a lot of different types of data sets. As you can see on the next slide, for example, on basically almost every day, we're dealing with information like pictures or movie, audio, and so on. Next slide. And for example, everyone knows JPEG. And the idea behind JPEG is really that you only contain in a picture what's visible. So you basically really cut out the parts that are not visible to the eye. So like, let's say the false information, because you can't perceive it anyway. Similar to MP3, you basically cut out things that your ear can't hear anyway. And so the question really is like, how do we do something similar for climate data? How do we cut out the parts that are not known, that are uncertain, that do not contain real information? And we've applied this to next slide, to the Copernicus Atmospheric Monitoring Service, CAMS, which concludes more than 60 atmospheric variables. So there's things like nitrogen dioxide, ozone, there's sulfate dioxide, there's various different types of aerosols in there, and I've just plotted 2 examples here on the right that you can see, which contain a lot of different information. So for example, nitrogen dioxide at the surface even contains ship traces, right? So you can see basically where ships have been going from one continent to the other, leaving behind these nitrogen dioxide emissions. And if you go further up in the atmosphere, you can actually see the imprint of the sun. There's a lot of turbulent mixing going on, and so on and so forth. So it's really difficult to estimate what actually are the uncertainties in these data sets. And we basically wanted to tackle this and try to find a way to estimate these uncertainties. These data sets, there's a lot of data produced. So ECMWF's data production is around 200 terabytes every day. That's 2 gigabytes per second. And it will probably even quadruple in the future whenever ECMWF is ready to go towards a 1 kilometer global model. At the moment, we're at about 9 kilometers, but hopefully that will increase in the future towards more reliable predictions of weather and climate. CAMS is only a subset of that, but CAMS still produces about 600 gigabytes per day. So it would be amazing to find a way to automatically identify what's real, what's not, throw away what's not. And on the next slide, I just want to illustrate that quickly. So imagine you have a data set, and we just take a little chunk here. You have some numbers in there, and just as an example, it could be these numbers here. So you can see basically all of these numbers have somehow in common that 0.05, and then something behind there that is different for all these different values. And this is basically then how we, for example, encode any kind of climate data into numbers. However, what's actually represented on a computer are bits. Next slide, please. And the only thing you have to know about this encoding into bits is that in the same way as the most significant digits for a decimal number are on the left and the lesser significant are on the right, the same holds also for the bits. So basically every row here on the left, very left, is the sign bit. On the very right, and you can see this, how basically at some point the bits try to start to be somewhat random and not really, there's no coherent pattern anymore. And then next slide. The same idea basically applies as for the example that I've provided earlier, that we somehow assume that the left part contains real information. However, at the right, at some point, the bits are basically just random and there's false information. So the aim is really to find a way to objectively separate the real and false information. If one knew the uncertainty, so in the example of getting from London to Paris, you have some prior knowledge. You know roughly how big London is, so where someone could live in London. But in general, we do not have that information. Of course, if you think about back to the talk that Alba just gave, there are people that try to understand what the uncertainty, where are the errors in these data sets. But in general, it's a really challenging task, and it would be great if we find some kind of objective way, some kind of shortcut that would actually allow us to do data compression more efficiently. And this shortcut that we found is using information theory, especially mutual information. And because mutual information is probably, might be an intuitive concept for some, but still it is an actually quite well quantified concept. I want to give you a quick introduction to mutual information in order to illustrate how we solve this problem. Next slide. Imagine the following example. You observe 3 different situations. So you look out of the window, you see the wind is because of there's a flag, you see wind is coming from the east and there are sailing boats out on the sea. The other situation is there's no wind and you see no boats. And the third situation is there's wind actually coming from the west and you see sailing boats. So the question really is what is the mutual information between observing the boats and observing the flag? And if you know one of them, could you also infer something from the other? Next slide, please. And that's really interesting because many people have an idea of what correlation means. But the really important point is that correlation is not the same as mutual information. So in this situation here, what we have is that from the known fact of that there are sailing boats, we can infer that there's wind, but we do not know the direction. because we don't know the direction, these two variables are actually uncorrelated. However, we can still infer some information from that. And so vice versa, knowing that there's either east or west wind, we know that there will be sailing boats, but we don't know, like, we know this for both, but still the direction is kind of like the unknown factor here. And then for the situation of no wind, we also know that there's no boats, which also holds the other way around. And this is exactly what we have applied now to the data. And the data, really, what I'm talking about here is zeros and ones. So you basically have this massive set of zeros and ones, and you try to infer the mutual information. Next slide, please. And so the way we did this is that if you take any kind of number, we encode it into bits, or like it is always encoded in bits if you have it on the computer. And what you do is basically you try to estimate the mutual information. So how much can one bit tell you about the next bit? And next can mean in any kind of spatial or temporal dimension. What can this bit tell you about the other one? And if there is some mutual information, even if it's really, really small, then we define this as real information. And whenever the bits are completely unrelated, so there's no mutual information, we define this as false information. And this is basically what's shown here in this graph, that the bits that are used to encode this are basically then just like a split, and we basically get, for every bit, we get a information content somewhere between 0 and 1, whereas 1 is then the maximum information you can have. And once you have this distribution of information, you can basically just find a threshold here. And this threshold then, for example, here would just tell you these are the bits that do not contain the real information. So ideally, you would round them, and rounding again, and basically in the same way as you did for the London-Paris example. We apply this rounding, set the trailing bits to 0, and basically only have to encode what's real and can throw away the rest. If we apply this to the whole CAMPS data set, as you can see on the next slide, this gives us quite an interesting picture. Interesting because on the x-axis now you have the different bits, and on the y-axis you have all the different variables that are in CAMPS. And this is interesting because the first thing that you can see is the required precision for every variable is generally different. So meaning that if you use some kind of standard, like let's say, I don't know, let's preserve 3 decimal digits for all of the numbers, this will not be accurate because some variables you may actually truncate some information. For other variables, you will encode much more information than there is actually in the dataset. And so the idea is really to have the compression methods that automatically adjusts to the number of real informations that there are in the bits. And this is basically what we've done, as you can see on the next slide. For example, apply to a satellite data set. This is just to show what happens if you use really high resolution image. Next slide, please. And so basically the question I want to ask you now is, can you even see which one is compressed, meaning 15 to 20 times smaller than the other? This is a satellite image of brightness temperature over Turkey and the Black Sea. So the country in the middle bottom is Turkey. And I guess in many cases, no, you can't really see it. And this is exactly the idea that basically, because we found a way to compress climate data, is very, very similar to the way how we actually compress images. This can also be applied to different, next slide. In order to understand what this, we call it information preserving compression, actually does, is I basically zoomed into this picture, and you can see. And the situation now that we have is that in the bottom left panel, at the top left panel, you can see there's a lot of like grid scale noise. So this is basically noise that is picked up by the satellite, is not really fully accurate. And so what this information preserving compression now does is basically, because it finds the bits that are only contain false information, you basically get a filtered version of what you can see in the top left, in the top right. And so it filters out the noise. And you can see this, that there's basically patches of like uniform values because it's not significant what the differences are in there. And this is even amplified if you would look for the gradients in temperature. So this is surface temperature here. What you can see therefore is like fronts, meaning that there's colder waters coming from the Black Sea mixing in with the sea just south of Istanbul. And if you look at the original temperature data set, there's always some gradients, whereas then once you apply this information preserving compression, it basically tells you there's a lot of areas that are actually insignificant, where we cannot say that these values are different. And so it basically removes insignificant gradients in your data set. The same idea of this information preserving compression can also be applied to different types of data sets. So as you can see in the next slide, this is something typical that you can find on your weather app, where if you look for your rain radar forecast, so basically if you want to know where exactly in the UK it's currently raining, this is a picture that you would get. And so in the two left panels here, there's basically a massive amount of rainfall over Scotland. And if we compress this, there's actually, well, you still can't really see a difference because you just remove the information that is false anyway. You preserve the stuff that's real. And so really what we want to see here is that the picture doesn't change. And it works for winter precipitation as well as summer precipitation on the right. And especially if the data is really patchy, there's a really high compression factor that you get, because you automatically filter out everything that's like insignificant information, and that's basically everywhere where it doesn't rain is really easily compressible. As we can see on the next slide, and this is now actually applied to data from the CAMS data set over the whole globe, going from 100% preserved information on the left to something like 80% of preserved information on the right. And this is really just showing where, once you start truncating some of this information, what the effect is of this compression method. And I'm not advertising that you should only preserve 80% of information in your data set, and you can see that things look really like in cartoon land. But it basically shows you that you can easily preserve something like 100 or 99% of information without actually sacrificing any of the real information in the data set. However, and this is the little numbers on top of the preserved information, the compression factor, you can see how the compression factor suddenly increases once you start losing your preserved information. And so usually the values that we aim for is something like 99% preserved information, and then you get often compression factors of 40, meaning that your data set is suddenly 40 times smaller, where you can store 40 times as many data sets with the same space available. Yeah, and so this was a great project that I really enjoyed working on. There's still some details to be solved. We're still thinking about ways how to efficiently implement that, especially for ECMWF, but the concept is out. And so as you can see on the next slide, I'm very, very happy about this, because we basically spent the last year also writing this up. And so we have this publication accepted now. It's not in review anymore. It's accepted in Nature Computational Science, which I'm really, really proud of, with Miha, Juanjo, and also Peter and Tim. And so if you want to have any more information on that, just probably give it a few weeks. There will be a nice open access publication out. And for all the technical details, please just go to the different repositories that I've been creating over the last 2 years, actually. Yeah, you find more information in there of how to estimate this real bitwise information content, how to do different types of compression. And for any questions, I'm very happy to answer them. Thank you.
Many thanks, Milan. Very impressive, your implementation, and congratulations for the publication. Ivan, very, very
thank you.
Media. So we have a question for you in a slider.
Yeah.
Do you know why CAMS model data are stored with so many decimals?
Yeah, so this is a typical problem that we're currently facing, which is that a lot of variables in CAMS are concentrations. Concentrations meaning that most of your values are somewhere between 0 and 1. In many cases, you actually have a few point sources, meaning that, for example, if you look at some of the emissions that, for example, are created by industrial activities, are very, like, you have a lot of, like, you have high values in very small areas somewhere scattered around the globe. And then because of the atmospheric circulation, it basically gets mixed, meaning that some of the concentration in some like remote locations really high up in the atmosphere can be really, really small values. And so in order to not sacrifice any accuracy on these very, very small values, as a default, and this has probably been started years ago, people have decided, okay, in order to not sacrifice any accuracy, we'll just go for something high because we don't know yet. And this was basically the start point where we started, because we wanted to know, is there less accuracy, less precision that we can go for? Where can we actually sacrifice the precision? Where's the precision not real? Where does the precision, additional precision, where does that not contain information? And this is why we came up with this information theory approach.
Many thanks. Many thanks. Now there's no more questions. We can continue now with the third project. The project ESO Project 2021. It is formed by 4 members from Italy and India. The name of the project is MaLePoM, you can see on the screen now, and Machine Learning for Pollution Monitoring. So the team is formed by Niccolò Brunello, Vitor Mittal, Paolo Fononi, and Luca Rampini. So I hand over to you guys when you are ready. Thanks.
Thank you, Esperanza. It's my pleasure to introduce you to our project, MaLePoM, which stands for Machine Learning for Pollution Monitoring. As you can see, our project is trying to deploy machine learning techniques to predict emissions, in particular NO2 emissions and CO emissions. A brief introduction about our team. Next slide, please. So I am Luca Rampini, a PhD candidate from the Architecture, Built Environment and Construction Engineering department at Politecnico di Milano. And my teammates are Niccolò Brunello, which is a master student in computer science and engineering, Paolo Fornoni, which is a master student in mathematical engineering, and Vitor Mittal, who holds a bachelor in physics. So as you can see, we are multidisciplinary teams with different backgrounds. So let's dig into our challenge. So basically, worldwide, the presence of nitrogen dioxide emissions is very important and has a lot of influence on human health and climate. These emissions are very correlated with anthropogenic activities, and nowadays, currently, there is only inventories that usually take in count these NOx emissions. These inventories have in particular 2 principal caveats, which are the first one, they are fixed or vary at a very long time scale. And the second one, they cannot capture slight variation such as diurnal variability or season-specific activities, for instance, traffic or burning crop. Next slide, please. Okay, so we divide our project in 6 main phases. So the first one is the data selection. So since a dataset for our purpose didn't exist, we explore many features and datasets available, in particular from Wikio, and we select the most promising, thanks also by the suggestions gave by the mentors. After the selection of the dataset, we explore better with the exploratory data analysis the features that we select and see how they are compatible with our target data, which are NO2 emissions. After that, we make some data engineering and we start to define our machine learning model. The last 2 steps comprises the publication of the results and also prepare the documentation that is available on the GitHub page of the project. Next slide. Okay, now we'll see in more detail the methodology that we used to perform the project. So the first part is more related to data science. So I will stress that there is no existing data sets to predict NO emissions. So the first step, which it takes one big part of this project, is to build and select different features and build a unique data sets. Then we did the exploratory data analysis, as we said before, and with data cleaning, correlation, and feature engineering, we select the final and data set that we used for training the models. For the machine learning part, we start with a baseline model to use as a comparison with our more advanced and complex model, which uses recurrent neural network. So it is a long short-term memory model to predict the emissions. Next slide, please. So the aim was to find the suitable proxy for emission globally, to predict emission globally, but we have to deal with some limits and bottlenecks, in particular computational power, because we have a data set with millions of records, so it wasn't possible to deal with a global data set, but we try to focus on a specific time and geographical location. And in particular, we focus on an area in Central Europe with a resolution of 0.25 per 0.25 degree. And we concentrate on the 3 particular months where we had the target data, so the emissions, which are May 2019, July 2019, and May 2020. Moreover, the data availability was another limit or issues that we have to face, because not all the features that we select were available on Wiki, for instance, the traffic. So we had to deal also with this limitation. Now let's start to explore in more details the different phases of our project. And so I leave the stage to my teammate, Peter.
Thank you, Luca. So the first step is the creation of the data set, as Luca was mentioning. So the data we use in our project comes from various sources, primarily from Wikio, which is a source of lots of geospatial and climate-related data. And also some data sets are sourced from elsewhere, for example, here, which is a company that provides real-time traffic data. So we select data sets based on various conditions. So one is obviously the geographical availability and coverage of the data set, as well as the granularity and temporal resolution, as well as the scalability. So it has to be available for the entire globe for a model to be applicable on a large scale. So in the end, we select 4 final data sets to use in our model, which are the concentration of certain trace gases in the atmosphere, which is obtained from the CAM's global reanalysis and accessed through Wikio. Then we have weather-related parameters like wind, temperature, precipitation, etc., which is again obtained from Wikio, accessed through Wikio. Then we have land use and land cover data, which gives us information about different land use classes, which is obtained from the Corin land cover data set, and again accessed through Wikio. And the final data set is traffic, real-time traffic conditions, so traffic density, which is obtained from the Here Traffic API, which allows you to query traffic data in real time. So these are the 4 data sets that we use. So another important consideration while or before building the model is the choice of dependent variable. So initially, the plan was to use NOx as the dependent variable in our model, since NOx is an important anthropogenic pollutant. But after starting, we observed that NOx concentrations in the summer months tend to be very unstable and unstable because of high photochemical activity that NOx experiences. So this made modeling NOx particularly difficult because concentrations are very depend a lot on photochemical activity. So then, after discussing with our advisors, we were suggested that we can use carbon monoxide instead of NOx to build the model initially, because carbon monoxide does not have such high photochemical activity, so it's more stable, especially in summer months. So then we built our model on CO, and then later we compare results for CO and NOx. Next slide, please. Yeah, so the next step in the project was to conduct some basic exploratory data analysis and try to figure out what features might be relevant in our machine learning model to predict emissions. Next slide, please. Yeah, so the first data set which we explored is the emissions data, which is the dependent variable in our model. So we find that the emissions data for our particular area which we considered, it had, or it seems to have, a couple of outliers or points which may be reflective of some erroneous values. So from this plot on the right here, we can see that these 2 points, the orange and green lines, represent 2 points for which the values of emissions are consistently much higher than the emissions or the mean emissions at the other locations. So it's almost 1 to 2 orders of magnitude higher throughout the entire time period. So these are probably, outliers that we have to deal with while or before building our model. So that is done by either dropping them or including that explicitly in our model. So next slide, please. Yeah, so the land use or land cover data that we obtained from Corinne, so that is actually an important spatial predictor for emissions data. So if you see the figure on the right, the top figure gives us the mean CO emissions for the month of May 2019, and the bottom figure gives us the percentage of built-up area, which is not temporally changing, but it's for the same location. So we see that there's a in general good agreement between the emissions and the percentage of built-up area, which is as you would expect, as urban areas tend to emit much more CO and NOx than rural areas. So it's important to note that the land use and land cover data, since it's temporally fixed, it only provides information about the spatial distribution or spatial variability of emissions rather than the temporal variation. Next slide, please. So an interesting data set to look at was also the traffic data. So we know that emissions typically follow a strong diurnal cycle, which has 2 peaks typically in the morning and evening. So in this plot over here, we see the orange line, which corresponds to the emissions profile, diurnal profile. And then looking at the traffic data, we find that the traffic very closely matches this diurnal cycle of the emissions. So the 2 blue lines here are the traffic diurnal patterns of the traffic data for 2 different points. The higher line is for Milan, and the lower line is for a point outside of Milan. So the peaks of the traffic match pretty closely to the peaks of the CO emissions. So we find that traffic is a potentially good proxy data set, which can effectively capture short timescale temporal variations in emissions. Next slide, please. So now to talk about the other data sets and the models that we used, I'll hand over to Paolo. Paolo.
Thank you, Vitor. The third dataset we will talk about is the concentration dataset. Here we have the data of some concentration of some gas in the atmosphere. And this dataset is very important in our model because we have the concentration of CO and NO2, which are the 2 gases that we're trying to predict. Managing this dataset, we can see that in some area, the concentration and emission are really good correlated, and so this dataset is also more important for our prediction. In the next slide, we will talk about the last dataset, the weather dataset. Here we have some features like the cloud, the humidity, the temperature, and to make a better correlation between this feature and the emission, we take the total wind, the temperature, and the humidity, and we shift this data some hour behind. In this way, we get a better correlation, and this will improve our model. Now we have all the data set we need. We can merge all this data set, create the big data set that we will use in our model. Next slide, please. The last part of this presentation, we will talk about the machine learning model. But before talking about the model we will use, we need to talk about the baseline model and also about the feature import analysis that we did. For the baseline model, we decided to use a linear regression. We used this model because we didn't need to pre-process the data, and we use a tenfold cross-validation. In this way, we can get some more meaningful value for the two statistical measures that we will use, which are the R square and the mean square error. For both the baseline model that we did, we got significant value for the two measures, but we can see that for the CO baseline model, we get better value, and this is one of the reasons that why we decide to put our effort in the predicting the CO than the NO2. In the next slide, we will see the feature importance analysis. From the graph, we can see the importance of the features using the Gini index, and we get that the most important features for our model are the land features, the traffic, and the specific humidity. Now we can start to talk about our final model. Next slide, please. Here we can see a framework for a generic machine learning model. We have some data, we put the data in the model. The model creates some predicted value, and we use this predicted value and the true value in the loss function to get better regressor, a better model, and a better prediction. This is a general pipeline for a machine learning model, and now I leave the floor to my colleague Nicolas, who can explain how we implement this framework in our project.
Thank you very much, Paolo. So let's take a closer look at our particular machine learning model. Starting from the input data, we can notice that they are both spatial and temporal distributed. In other words, the dataset lays on a three-dimensional space, which raises the complexity of the problem. Moreover, there is a large discrepancy among the range of features, especially the target emission values. But this is something that standard processing techniques can easily solve. In second place, we explored many different models, and we came to the conclusion that neural networks are the most effective techniques, and in particular, recurrent neural networks, as my colleague said before. But the problem with this model is that they are really, really complex and takes a long time to train. Last point is about the evaluation of prediction versus ground truth. So apart from choosing the loss function, we face the issue on how to evaluate our results. As we explain later, we decided not to rely only on the value of the loss function, which the lower it is, the better it is, but also graphically visualize our results in order to have an idea of our performance. So next slide, please. So this is an example of how data were presented to us. As you can see, the dataset is indexed by both latitude and longitude, and for pair of them, it contains all the time sequences. So we adopted two training methodologies. The first one is the basic training, so selecting random subsequences from data and feed the model with them. But we noticed that in this way, there's some probability that subsequences take into consideration far away locations together. So in order to solve this, we can create a custom training, we call it like that, which basically force the training to select subsequences from the very same location. So next slide, please. As you can see from the slide, we tried 5 different final models. So the first is the empirical mean, acting as a baseline, of course. And then we have a standard neural network trained with a basic training technique, then another standard neural network with a custom training, then more complex, the recurrent neural network, long short-term memory with the custom training, and then finally with the recurrent neural network with the principal component analysis applied on the dataset. The best performing model is the fourth one, as you can see, which raised the lowest mean square error on the test set, computed on the test set. With this procedure, we saw that the best, but we want also to know somehow how much is our error in making predictions. So in order to do this, we plot data. So the plot on the right side you see is the plot taken from the best performing model of a subset of the test set. And in orange, there is the prediction. In blue, the ground truth, and in red line is the empirical mean. And as you can see, data prediction are quite imprecise. The error is quite high, it's not sufficient, but our model is quite able to capture the variability of the emissions, so the diurnal pattern and also the week pattern. So from this result, we can draw some conclusion. Next slide, please. First of all, we are quite satisfied with the dataset created. Since there is not similar project online, we had to create it from scratch, and it shows good potential to tackle the problem. Also, the models show a good pattern matching with the mission, but of course, right now it lacks of precision and single point prediction, which are the bad results still working on it. So for this reason, we strongly believe that our project is a starting point, since it shows promising result, which could be improved with the next steps. Showing the next slide, please. In particular, the bigger challenge here is to gather more emissions data, which are really rare and difficult to get, but having more data could lead to better precision and also pattern matching with seasons and years. Also, more hyperparameters tuning and more complex models should be followed, but the former require a lot of time and the latter requires large datasets. And possibly also explore and find out more reliable proxy data could be a way to improve performance. So next slide. So thank you all for the attention. We'd also like to spend a special thanks to our mentors who constantly supported us and guided us in this project, and also in all the people involved in the challenge, which gives us the wonderful opportunity to learn and get in touch with such advanced and promising reality. Thank you.
Thank you, MaLePoM, for this full and very interesting talk. And a pleasure for you to take part in ESoWC, for your motivation and enthusiasm. So please, I encourage everyone who wants to raise a question, go to Slido and include the event hashtag ESoWC 2021 and type your question. There will be 10 minutes at the end, 10 minutes for the question and answers at the end of these afternoon sessions. So the next and the last and the next project of this edition of 2021 is AQ bias correction. The team behind this project is Antonio Pérez Velasco and Mario Santa Cruz Lopez from Spain. And they are going to explain to all of us this project.
Thank you, Esperanza. Good afternoon, everyone. My name is Antonio, and I'm here with Mario to present the results of our project, Air Quality Bias Correction, corresponding to ECMWF Summer Weather Code 2021. Before going ahead, I would like to thank our mentors for their support and expertise throughout the project. Thank you, Johannes and Mija. Next slide. For those who attended the midterm webinar in July, you will be familiar with the next couple of the slides. However, it is important to mention that air pollution affects worldwide population with an estimate of 7 million premature deaths, according to the World Health Organization. These air quality forecasts are necessary. Not only are they crucial for informing citizens about their exposure levels, but they are also vital for supporting policymakers on their daily tasks. In the next slide, we check that these forecasts, as shown in the figure, are biased systematically. In this case, a negative bias is shown, which makes the model underestimate the real observations. This is an important problem. As a consequence, these forecasts need to be corrected in order to provide these people we mentioned before with data as accurate as possible. Now I will leave the floor to Mario, who will talk about the modelization and validation approaches.
Thank you, Antonio. Now, in this next slide, we will present the general workflow. It has been divided into several phases. First, during the pre-processing stage, we have converted the forecast and the observations available into a structured dataset with features and labels. Then we loop between the modeling and validation stages until a satisfactory solution for forecasting the error in the predictions has been reached. Now we move to present the final model architecture in the next slide. In this case, we have considered 3 different models to extract the most meaningful features of the past and future counts predictions, as well as the station attributes. Regarding the predictions, an inception time model has been used for both the past and the future predictions in order to exploit the temporal variability, whereas a multilayer perceptron is used for the station attributes. Then, all extracted futures are fed into another multilayer perceptron to predict the upcoming errors with early resolution. In the next slide, we will explain that we have considered 5 different initializations. Please go to the next slide. Yeah, here we explain that we have considered 5 different initializations of the models considered. Each of these produces a different model that outperforms the CANS model, and all 5 models are assembled with equal weights to have a stable final regression, which reduced the error matrix by around 35%. A model with better performance corresponding to including the latest observations as inputs was discarded during the project development. This was made to facilitate its future integration with the CANS model. This model achieved a reduction of almost 55% of the error matrix. Now we move to the next slide, where we present how the data was managed during the validation phase. First, the dataset was split in 2 different periods of time, one for training and one for testing. For both of these periods, we compare the air quality predictions corrected with the raw CAMS predictions, the observations, and the persistence, which refers to forecasting each day the observer's value of the previous day. This constitutes the validation dataset. In the next slide, we present a slice of the validation dataset for the ozone at the station located at Glasgow. Here, the error metrics for each approach can be easily computed in order to assess the performance of our model. In the next slide, we include some validation plots for the same location, the Glasgow station. In the left plot, the hourly distribution of each variable is represented by a box plot. Here, the blue and green boxes represent the original and corrected CAMS predictions, whereas the yellow ones correspond to the observations. It is clear that our model improves the CAMS forecast significantly, but it does not reach the persistence. In the right plot, the cumulative distribution function of the hourly errors is presented. Here, it is clear that the overall bias is reduced because the CDF is shifted to the left, to where the zero is located. These plots are generated for all air quality variables and locations for both periods considered, the train periods and the test period. And now we move to the next slide, where in addition to the validation plots, we have also considered different error metrics. For example, during the validation phase, we have considered error metrics with respect to different time periods. Some of these error metrics were the residuals, the root mean square errors, the mean square error, the mean absolute error, and the error square coefficients. And now Antonio will explain in detail the result of the final model previously presented during the validation process for these error metrics.
So as Mario mentioned, if we can go to the next slide, as Mario mentioned, a set of metrics has been implemented to validate the results on both train and test data sets. In this slide, I'm showing you some of the results. This is the number of stations which present an improvement in both train and test sets in terms of the metric used. So we are showing a table where you can get information about the total number of stations for each variable. You can see that there are 61 valid stations for the NO2, 67 valid stations for the O3, and 102 valid stations for the PM 2.5. As shown, there is a bias correction, a successful bias correction of almost 80% of the stations in the worst case, which corresponds with the PM 2.5, and there are more than 90% of the stations corrected in the best case, which corresponds to the O3 variable. There's also an increase in the Pearson correlation, which we mean here to the skill of the forecast. In the worst case, 55% of the stations increase the correlation, which means that there is another 45% which decreases it. In the best case, which corresponds to the O3, almost 75% of the stations increase their skill. You can see more specific information about each station metric in the link provided in the presentation. Next slide. We have also checked the overall improvement for each metric in both train and test sets, which correspond, these values offered here correspond to the average of both train and test sets. You can see here that that overall the bias is reduced for every variable, and that the skill of the forecast is increased as well for every variable. There's an increase on a skill for the O3 variable of around 400%. This is due to the fact that it is strongly correlated with the hour of the day and the radiation, which are variables that are provided to the model as features. Next slide. Not all stations have an improvement, as shown in the results table 2 slides before. So we are showing here just an example of an station which doesn't improve the CAMS forecast, the raw CAMS forecast. This is the example of Vienna for the O3 case, in which we can check that the CDF shows the error is just centered at 0. So there's not much to improve. Next slide. Apart from that, we have developed an operational implementation workflow in which we start downloading the data from the atmosphere data store and process it in order to have the proper features prepared to fit our model. We load our model and afterwards prepare the predictions. So we have developed a near real-time operational workflow in which for an station and a variable, we can get the predictions in a fast and easy way. Next slide. With this operational workflow, we have run the simulation for the August 2021 month at Glasgow. We can check that the bias has been corrected and the skill of the model has been increased as well. So this is an example in which I mentioned like a successful case, but there are also unsuccessful cases. If we go to the next slide, we can check that for Montreal there's also a bias correction for the CAMS model comparing to the observations, However, the skill in this case is not increased. In this case, the skill of the cams of the raw cams is better than our prediction. If we go to the next slide, here for the case of Budapest, for the NO2 variable, we can check the same situation. There's a bias correction of the raw cams forecast, but the skill is not improved in this case. Going to the next slide, we can check a case in which we don't correct the bias, but we increase the correlation. As we mentioned, the O3 variable is strongly correlated to the radiation and to the local time hour. This is why we get the diurnal cycle very well in this image. The correlation for this data goes from 0.79 to 0.86, even though the bias is not corrected. And I leave the floor to Mario in order to explain you the conclusions.
Yeah, here now we move to the last slide. We try to summarize here the key points of the project development. First, one of the main features of the solution proposed is that a unique model is considered for all stations. One advantage of this approach is that it can be easily extended to new locations even without air quality stations. Another key point is that independent models are considered for each air quality variable. Additionally, the period considered for training includes the COVID-19 lockdowns, which increase the stability of the model as it has been trained with heterogeneous scenarios. Another insight extracted while working during this project is that including the local time at each location allows the model to capture the diurnal cycle of the air quality variables, which clearly improves the model performance. Lastly, the model seems to provide robust predictions even for different CAMS model versions. Here, the model has been trained with a different model version than the one used for the evaluation phase. And to conclude, thanks again to our mentors, and remember that all the code implemented for these solutions, for the processing, the modeling, and the validation part, are available in GitHub. Antonio and I will be very happy to answer any question you may have. Thank you very much.
Thank you very much, Antonio and Mario, for your presentation and your exciting results. So now we have two questions for Milan. Milan, are you there? The first question from us is what false and true information not dependent on the perceptual capabilities of the observer?
Yeah, I think with perceptual capabilities, you basically mean the kind of like the rule of thumb that I've presented is that if you can't see a difference in two data sets, then there is no information that's actually lost. Well, this is more rule of thumb and not like necessarily the a general law. There's still like a lot. Basically, there is some truth in this. However, in order to answer your question in a more general case, I think what we try to understand is how this concept of real information, as we have defined it, how much that actually depends on the use case. So if you remember this graph that I had with like 100% preserved information on the left, and then going down to like 80% preserved information on the right. The situation we're here in now is that actually you can, of that information, you can cut off quite a lot without actually sacrificing the mean. So that the mean of this data set would not have actually been affected, even though you could have like cut off a lot of information. So if your use case is you want to somehow preserve the mean and make some kind of, I don't know, climatological assessments of the data, then your real information that you need is actually a different one compared to, let's say, you want to have like a specific point and you want to have the forecast as a specific point as accurate as possible. And so, yeah, really understanding all these different use cases and finding basically one way to define this real information for all of them is tricky, especially because there's like a lot of subjective choices in it. There might be a lot of different use cases, and people may say like, this is important for me, this is important for me, I don't care about that. And so, as far as we have understood it now, the definition of the real information content as we have presented is a rather careful one, trying to include most of these use cases. And we're basically still looking for use cases where our definition of real information content does not actually apply. So if you have an idea of something that might be really difficult to compress, please approach me. But I think at the moment, we're basically trying to include as many use cases as possible. And we hope that our definition is good on that, but it definitely needs more time to understand the specifications here.
Thanks. Peter has another question for you. Can you give a sense of the computational resources time required to perform these compressions?
Yeah, so the techniques that we've looked at are basically all at least on the order of that they can compress 100 megabytes per second or faster. While we haven't really looked into all of the details of the different performances, we basically wanted to have like a sanity check that if actually we were like operationally produce a lot of data and we would run the same amount of compression technique that we're presenting, that you can basically compress things in real time, right? You don't want to like, I don't know, end up waiting because your compression is not fast enough. And so we kind of use this 100 megabyte per second. You can get higher compression factors if you would actually use higher levels of like basically there's a little bit of a trade-off still that you can exploit if you wanted to. But in general, we kind of like aim for this like 100 megabytes per second, but to have that at least. But yeah, this is there's definitely more research needed to find like in case there's a data archive where speed is really important to find the best solutions. We kind of neglected that and looked more at the precision and the volume instead.
By the way, Peter sends you a smiley face. Super presentations, he says.
Thanks.
Okay, so we are reaching the close of this virtual event, the Final ESoWC Day 2021. But before that, I'm very pleased to introduce to Stan Vermont, who is the head of user engagement section in Copernicus at ECMWF, and he will give us a short final close from Copernicus and maybe give us a very short overview about the program. Stan, the floor is yours. Okay, we are very pleased before solving these technical issues. I would like to say a big thank you. Next slide, please. A big thank you to the mentors. You can see 23 names visible on the screen. These mentors have been guiding the teams along the ESoWC journey, and without your expertise, free time, enthusiasm, motivation, and amazing project, the amazing project results we have witnessed today couldn't have been possible. You heard a very kind words from the participants. So ESoWC is a teamwork, is for sure. So I would like to give you a very special thank you to all of you, which are Copernicus and ECMWF staff. We are very pleased to say that and to announce that the 5th edition of the ECMWF Summer of Web.co is coming soon. Will be the 5th edition 2022. So please visit our website to learn more about the new edition. We post regularly on social media, so Twitter is an excellent source to get informed. For all updates, you have the option of ESoWC newsletter. So register now and you will receive the latest, so you won't miss anything. To those who couldn't attend the first or the final ESoC day, and also these afternoon sessions, there will be recordings, so they will be available from tomorrow. And please check our ESoC YouTube channel. You will find all the presentation, individual presentations there. Okay, so we'll see if Stein is available now. Okay, so it will be a pity, but he will express our closer from Copernicus. So that's all for me.
Does it work well, Esperanza?
Oh, yes, we can see you. We can hear you.
Sorry.
Welcome.
Yes, sorry. I'm staying remote indeed. I'm based in Bonn, and I have to say that we just installed some new microphones today, which messed up my default setting. So my apologies again for this. I want to say a few words of thank to all the teams of the organization team. And I want to say a few words about Copernicus itself. So most of you know Copernicus. It's the Earth observation program of the European Union, for which we implement two services. It's the atmosphere and the climate change one. And we also operate the computing center for emergency management linked to floods and fires. Copernicus is open and free. We have lots of users. We are approaching 100,000 users at the moment. We have more than 90 different data sets, and about 70 terabytes of data is downloaded every day. So it's very focused on operational data provision, and that's what we are focusing on at ECMWF. So we are very focused on specific objectives to develop these data services, to develop the infrastructure, the data processes, the documentation, and user support. This unfortunately leaves us with little time to focus on other things which really are essential to keep us advancing with the new technologies, with new knowledge and things like this. And that's why an initiative like the Summer of Weather Code is so crucial. Your input is so crucial to test new ideas, on post-processing, to improve how we do our modeling, to test some new ideas on data access. We also have seen this to improve applicability, and to create added value by combining different data sets. And that's, I think, one of the nice things several of the teams have done, is to combine different data sets. So Copernicus and non-Copernicus. And that's something on which we really need to advance, because that's in fact the future, to create added value out of it. So thanks again to all the teams for the interest, for all your efforts to create added value out of Copernicus. And I hope that the collaboration with my colleagues, the different mentors, was very rewarding. I really look forward to see some bright minds again next year, because we just signed the contract with the European Commission for Copernicus 2. So this paves the way, in fact, for another 7 years of funding. And this will also pave the way for a continued supply of the existing data sets, but also several new ones will pop up. So Copernicus' role in the Summer of Weather Code will remain. We will increase our inputs in the future, and I really hope that with the new challenges which are upcoming in the future, we will see a lot of interest from you and from some new people. So thank you for your contribution.
Thank you, Stein. Thank you very much for all that took part in ESoC 2021, sorry. And if you want to have a go, please, are welcome to take part in the new edition, the 5th edition. So that's all for me. I hope ESOC has been a fruitful coding experience for all of you. Thank you very much. Bye.